differential equations. We're starting a brand new chapter, chapter 5, and at least for the majority of this chapter, we're going to really focus on springs and setting up second-order differential equations that really will model the behavior that we'll see with a spring. Today we're dealing with undamped motion, and as we recall Hooke's law, as we look at undamped motion, free undamped motion, we're going to recall Hooke's law. Hooke's law is really a restoring force. You can see at the top of our note page here, as a weight is pulled down, the weight is going to be pulling in a direction. We're going to assign that direction to be positive. So downward is positive. There's a restoring force, the force that would be pulling in reverse, pulling upward in this regard. This would be negative. In this regard, that would be Hooke's law. Force would be some constant multiplied to the distance that the spring is moved. So what we can do very quickly is just take a look at three different scenarios. Let's come over here to case number 1, where we have a spring with no mass. We've got a spring, and it's coming right down here to this dotted green line. This is where the spring would normally hang. We don't have a weight pulling it downward. If we did have a mass attached to the spring, and if we let it come to rest, and rest would be considered equilibrium, what you would see is that the spring is now pulled below where it normally hangs. And of course, here we have the weight, and here we have the restoring force in red pulling upwards. So what we can see is we have a distance S that we would normally associate with here. So what we're going to see, and I'm going to put a little star here, we're going to see that the weight coming down, that's Newton's second law, mass times acceleration, mg. Remember, it's downward. We only have acceleration with the gravitational constant. But as we're looking at this, if we had S, as we come back up here, F would equal K times S, and it would be in a negative direction pulling upwards. We'd have negative Ks equaling 0. So we have the weight, we have the restoring force. That all works out to 0. Works out to 0 as we are in equilibrium. We don't want to forget about this. This is going to be very, very helpful as we proceed. So as we move on to this next case, of course, perhaps our weight is now in motion. And you can see I've drawn another black dotted line. This is where the weight would normally rest at equilibrium when the weight is coming to a stop. Up in green here, this green dotted line would be where the spring normally hangs. But of course, we can see a spring in motion bouncing up and down. So what we can see is perhaps this weight is going to go below the equilibrium resting spot, and perhaps it will travel in an additional x units. X would be greater than 0 if we're coming this way. This would be positive. X equals 0 would be at the equilibrium resting spot. And of course, S is that distance. But as the spring could be coming upwards, that would mean that X could be less than 0. So we just have this basic setup. Now, Newton's second law is really saying F is equal to m times a. And if we're looking at the position x that we have for this weight, we could say m times the second derivative for our a, or acceleration. We'd have the second derivative of x with respect to time. But let's make ourselves a little force diagram and think about what's really happening. We've got our weight, of course, would be contributing to this sum of forces. That would be mg. We're always going to have mg, the weight, pulling downwards. But then we're going to have our restoring force. That would be Hooke's law. And Hooke's law, of course, is going to be negative k, but the distance that we're going to have will be s plus x. If x is negative, of course, that would come into play. S plus some negative x value would be in an appropriate position. A negative, of course, because it's a restoring force pulling upwards. So let's go ahead and just distribute this negative k into play here. We'd have negative ks, and then we'd have plus negative kx. And I guess what I'd just immediately like to point out to you is that there's a reason why we highlighted that little expression in green over there. We saw earlier that mg plus negative ks was actually 0. So what we're seeing is actually that completely wipes out. And, then, and forgive me, I need to fix up where the square here for the second derivative is. That's d squared x all over dt squared. You can see this whole thing is 0, so we just have negative kx. So I'm going to bring this back down over this way and just continue to write. I'm going to bring over the kx. We'll have m, and we'll have our d squared x all over dt squared plus kx, and set that equal to 0. At this point, I hope you're noticing that what we really are dealing with is a second-order differential equation, something that we've already spent some considerable time on in our previous chapter. If I were to divide everything by m right now, we'd have d squared x over dt squared, that second derivative, plus kmx equals 0. But we're going to let omega squared equal k over m. And the reason why we're not just choosing omega, perhaps you're going to see why in just a moment, is that it's going to be very beneficial to have this coefficient seen as a square. Remember, it's just really a constant right now. We can think of it that way. But here's the whole reason why we're doing this. Last chapter, we solved a characteristic equation. And let's take a look and see what would happen if that were the case. We'd get m squared. Now maybe you can see why we wanted to think of that constant as a square as well. That's m squared plus omega squared equals 0. And where does that lead us? Well, as we're solving, we'll get m squared will equal the opposite of omega squared. And if we take our square roots, we'd realize we have complex solutions. We'd have 0 plus or minus I omega. We're taking the square root of something negative. So it is a complex solution. Hopefully you remember from last chapter what that characteristic solution is going to look like. Remember when we had m was equal to alpha plus beta I, we saw that the general solution would be E alpha t times a constant cosine of beta t plus constant 2 of sine of beta t. And what we can see right here is this is, of course, dealing with constant coefficients, and that's what has driven this whole process. We have a differential equation with constant coefficients. Well, if your alpha is 0, you can see e to the alpha right there, alpha t, that's going to be a 1. So we're going to be left simply with C1, and then we can very quickly see that our equation in this regard will be cosine of omega t plus the constant C2 sine of omega t. Very, very important equation right here. We're seeing this would represent the position of our spring with that weight attached at it, where that weight is actually located in this coordinate system. Now, as we continue, you're going to notice that both cosine and sine both have an omega t as arguments. You might remember that whatever is multiplied by the independent variable affects the period. So we're going to go back to some trig review and say that the period, of course, is 2 pi all over omega. And what that's really telling us is that's how many radians it will take to complete one cycle. We've got a cosine of an omega t plus a sine of an omega t together. They have the same general period. Of course, adding them together, we'd expect that the combined sum would have the same period. They do. We could call this t just as a simple variable. But again, it's that many radians per cycle to do one complete period. As we go ahead and take a look at the flip, the frequency would be omega all over 2 pi. That would be 1 over t. And that would be a cycle per radian. And sometimes it's more helpful to think about a problem in that context of saying it would be one cycle per so many radians. We're going to leave off here. This was our introduction. We're going to do one problem in our next video where we actually put this all together and see how it all works out.